All right, for today's lesson, we're going to be talking about optics, which is basically using mirrors and lenses to make images, and we can do useful things from corrective eyewear to examining things that are very small, as in the case of microscopes, or very far away in the case of telescopes. So the first thing in optics is to understand what a mirror is. So we've all seen mirrors, but what's the definition of it? A mirror is something that reflects light so that it can form an image. So lots of things that reflect light, actually everything reflects light, but most things don't form an image. When we're talking about the reflection of light, we are using the law of reflection. So the law of reflection tells us that as light comes from a source and hits a mirror, and when it bounces off, the angle that it hits at and the angle that it bounces off at are the same. Now, one thing in science that when we measure these angles, we don't measure it off the surface of the mirror. We measure it off of a line that is perpendicular to the mirror, which is called the normal line. And we do this because when we're talking about curved mirrors, they still have a line perpendicular to the curve, but it's hard to measure an angle off of the curved surface since the surface keeps changing. So as I said, mirrors are not the only thing that reflect light. There's actually 3 different types of reflectors. So a specular reflector is a type of reflector that a mirror is, where all the light that comes from one source all bounces off in the same direction, and that's how it's able to make an image. Other types of things that reflect are not as smooth as mirrors, and so they can reflect in different ways. Most things are diffuse reflectors, where light coming in bounces off in all different directions, so it goes all sorts of different ways, which is why we can't make an image. Some things that are fairly smooth, so you can think of like a smooth floor, like a smooth tile floor or the whiteboard, are a spread reflector where you get somewhat of an image coming off. That's what we call glare. So it's smooth enough to get some of an image coming, but it's not the clear, sharpest image because you still have light going in different ways. Okay? Oops. Ignore those lines. So we ask, is all the light that hits an object reflected? And the answer is no, as we've already seen that depending on what light gets reflected, what light gets absorbed, we'll get different colors of objects. So I'm going to talk about this here. We've already touched on that. Okay. So images form for a reason in a mirror. If I put my eye in different locations, and so this black line is a mirror here, and have an object, because of the law of reflection and the way the light comes in and bounces off, no matter where I put my eye is going to assume that if the light came from straight back into the mirror. And so no matter where I put my eye, all the light from this part of the object is all going to be coming back from that image point. And so that's why an image is formed, because no matter where I'm standing, I see the light coming from there. Okay? So one of the things we want to be able to do in this class is locating where an image is. So to do that, you're going to draw a ray diagram. So in ray diagrams, what you're doing is you're picking two rays of light and seeing where do they reconverge at, because wherever they reconverge is where the image is going to form. So I have a picture of a fellow here that looks like he probably spends a fair amount of time standing in front of mirrors. Okay? So if we look at where's the image of his hand going to be. So I take a ray of light coming from his hand, and an easy one to pick is one that's coming in perpendicular to the mirror, because anything that comes in perpendicular to a plane or a flat mirror will return perpendicular. So if there was an eye here, okay, to the eye, it would seem as if that ray of light came from back behind the mirror. If I choose another line of light, a ray of light, as it hits the mirror, again making it so it bounces off at the same angle. Okay, so remember off the normal, these two angles need to be the same. If there was an eye down here looking at it, the line of sight is straight back. And so because the two rays of light that left his hand appear to re-intersect, and no matter what ray of light I choose, if I draw it properly, so if I have another one that comes here and then reflects back up, if I trace it back, they all should come to the same place. And so that's where the image, and I didn't quite place this correctly, that's where the image of the man will be. Okay? On a flat mirror, we're going to find that this is always going to be from here to here. That's the same distance. Also, when we look at how high is the object compared to how high is the image, okay, they're going to be the same height. In fact, all their dimensions are going to be the same. Okay. Now this image here is called a virtual image, and it's virtual because it's not really there. The light doesn't really come back together. It only looks like it converges on that point behind the mirror. But obviously if I go behind the mirror, there's no light from that man that's actually going there. Okay. If you put multiple mirrors together, you can get multiple images. So with two mirrors put at perpendicular angles, we can make 3 images. So you can see when you look in the right mirror, you're going to get one on the right. When you look in the left mirror, you'll get an image on the left. And when you look right at the corner, an image can form too. So I want you to try to think about, like, what if you started putting mirrors closer together? How many images will you get? And we'll actually do a lab on that. Okay. So most of the mirrors we're familiar with are flat, but mirrors can also be curved. And so mirrors can be concave, which means they like cave in. And those mirrors are considered converging because light that comes in parallel goes to the focus. They can also be convex, which means bowed out. And when light comes in, it gets reflected outwards. So that's considered diverging. Okay. When we have curved mirrors, and we'll also look at the same thing with curved lenses, there's some different terminology in different parts of the mirror and the lens that we have to understand. And so those are here. So make sure you understand those, and I'm going to be using these terms in the next couple drawings. Okay. So for locating an image on a curved mirror, we look at, so I need to know where the principal axis is, because that's going to define how some of my light, the rules for locating the ray, and then where the focus is important. So I'm going to start off with a concave mirror. Okay, and I've just got this little sarcophagus thing here, and I'm going to pick 2 rays of light that make this easier. So one ray of light is going to come in parallel to that principal axis. And when something comes in parallel to the principal axis, what it does is it bounces towards the focus. Okay, so it's going to come back this way. The other ray of light that I'm going to choose is one coming from the direction of the focus, and that one always bounces back parallel to the principal axis. So now if I look at these 2 rays of light, they don't ever really come together. So if I had somebody's eye here, it would look like it was coming from back there. And if somebody's eye was here, it would look like it was coming from back here. And so because those 2 rays of light reconverge behind the mirror, I'm going to make an image of that behind the mirror. And it would be flipped around the other way, so just ignore that it's going the same direction. So again, this is a virtual image because they virtually come together. Okay. If I take instead and move this so it's outside the focus to begin with, and look at what happens now. So again, I'm going to choose one ray of light that comes in parallel to the axis, and again, that's going to bounce back through the focus. And now I'm going to take another ray of light that goes through the focus, and the rule is that bounces back parallel. And those 2 do really intersect, but now they intersect below. So now I am going to make I'm going to make an image and it's going to be upside down. So if we, whoops, I guess it won't let me do that. Transform. Okay, so now it's going to be an upside down image. And you might have noticed this looking at a curved spoon or something. This is a real image because it can be projected onto something. Okay, so now I got this like crazy fox man, and he's in front of a convex mirror. And with a convex mirror, the rules are the same. A ray of light that comes in parallel to the axis leaves in the direction of the focus. It doesn't actually go to the focus because in a convex mirror, the focus is behind the mirror. So it can't really go there. And then I choose a ray of light that goes towards the focus and it reflects back parallel. These two lines of light will never really intersect. They will virtually intersect back here. And so I will get a virtual image of the fox in that location. So that's what we can do with reflection. We've also learned about refraction, which is where light bends as it goes from one material to another. We can think of why does the light bend if you look at the waves coming in. If it's able to move fairly fast, and then the wave slows down as it gets into the new material. So if we think about like these waves being axles with tires on either side, if you can imagine as this tire here enters into the slow material, it will slow down, whereas the tire on the other side will keep going faster, and so that axle will rotate. So when we look at the rules for refraction, when you're going fast to slow, you bend towards the normal. And if you're going the other way, if you're going slow to fast, you bend away from the normal. Okay, so if it was going the other way, coming in, and then it would bend away. Okay. So that can lead us to some different effects. So if I'm looking at fish through the corner of a fish tank, you see a couple of them, and I see a couple cups. And if we look at Y, we see that here the light's coming out, and then it's bending away from the normal, and this light's coming out and bending away from the normal. So light that started off going two different directions ends up going the same way or towards the same point. So with my eye here, it looks like it came from two different places. So I'm seeing two different images of the same thing. I'm not seeing either one in the correct spot. So with light, we can also use curved lenses now, which are transparent materials that are curved. And so you can have a convex lens, which is now converging. So the convex versus concave doesn't have to do with what they do to light. It has to do with their shape. So convex means bowed out in either a mirror or a lens. So the convex lens, if light comes in parallel to the optical axis, it goes into the focus. And with a concave lens, light comes in parallel, it goes out away from that principal axis. So when I locate an image on a convex lens, again I pick my two rays of light. One comes in parallel to the axis, and it goes out through the focus on the opposite side of the lens. One comes from the direction of the focus, and it will leave parallel to the other axis. These two don't ever really come together. We can trace them back, and so the image of the sailboat or the parasailer would be back here. And it's virtual, okay, and enlarged. For a concave lens, the way we use the focuses is different. So I'm going to choose a line that comes, or a ray that comes in parallel. And now it's going to leave in the direction of the focus, but now it's going to leave in the direction of the focus that's behind the lens. So it's going to leave like that. And then I'm going to choose another ray of light that comes in towards the focus now on the opposite side. And that one leaves parallel. And those never come together. They only virtually come together behind the lens. And so you get another virtual image that's smaller. Okay? So we can use lenses and mirrors to make a telescope. So to make those, we always have to have two things: an objective that gathers lots of light, and then it makes it into a very tiny real image of the object. And then a second lens is called the eyepiece, magnifies that image so that we can actually see it, so it's not just a tiny little point. Okay. And here's a diagram of that working. So again, the first lens, this is the objective lens here, takes in a whole bunch of light, gathers it to one tiny little point, and then as that goes through the eyepiece lens, it spreads that image back out so our eye can actually see it. This is another similar one down here. This one uses a different type of eyepiece that's a concave lens, and that one will make it so the image doesn't turn upside down like it would in a other regular telescope. Oops, and I guess that's it. All right, so we'll be working with ray diagrams a lot in the coming days and doing some labs with mirrors and lenses.